One of the most similar is the standard DC to DC step-up converter. We see that it has a single inductor and a single transistor. And the supply here could be a battery or anything else. But in this case, instead of being triggered by a magnet going by, this is just triggered by some sort of pulse train. And instead of trying to kick the energy back to the initiating battery, what this is trying to do is actually build a charge to a higher voltage over here. So just by setting the circuit up in this way with a single extra diode, then the voltage can be multiplied from our initiating source. So this is another very simple one transistor, one inductor circuit which has energy kickback similarities to Roger Andrews. Now certainly no one has done more work on this simple little phenomena of charging an inductor, getting a little bit of motor torque out of it, and capturing the inductive collapse than John Bedini. This is the cover page of his 2003 patent for what he calls the monopole motor. And let me show you that schematic right now. So here is the design of what John calls the monopole motor. And he calls it the monopole motor because on the wheel here, that is the motoring member, only North Pole magnets face outward. And so this inductor is only being subjected to North Pole magnets, and the souths are kind of inside the wheel here, and they never interact with the inductor. So here we see that all of the functions are separated and distinct, so we can see the full action of this simple type of arrangement that was at least partially embodied in Roger Andrews' executive desktop novelty. We see a battery, and we see a number of coils on the inductor, and in this case there's 3 separate coils, and they're all wound tightly together in what's called a trifilar winding. So there's very tight induction between the windings themselves. We have a movable wheel here. Andrews used either a top or a little pendulum or something else, but John says no, this is just a wheel that has magnets on it and can be looked upon as a motor. And so what happens is that the magnet will come by here and magnetize the core, and when it starts leaving, what it does is it induces a signal in this trigger winding which turns this transistor on here. When that happens, the battery conducts current through the coil, through the transistor, and back, that same simple inductor transistor battery arrangement. And in this case it reverses the magnetism in here and further kicks the magnet out. So in this sense it works just like Andrews' silly little novelty. But now there's a whole provision here to capture the energy when the magnetic field in here shuts off. And so here we have a third coil connected across a full wave bridge rectifier to charge this little capacitor. The idea ultimately is to charge this battery, and so when this capacitor gets up to a certain voltage above the battery, then a little, some sort of little timing mechanism, this is shown as a commutator in brushes, will drop the contents of the capacitor onto this battery. So this battery charges, the motor motors, and this battery runs the situation. So here we see the beginnings of an understanding of what we thought might be possible when we saw how an ordinary motor works. In other words, there's an electrical input, there's a mechanical output, but there's also an electrical output. And now here we see the topology where all of these things are working as stated, all in the forward direction, so that we can really understand these things very clearly. So here we have a simple diagram where we show all four of these ideas right next to each other. First, over here we have Roger Andrews' simple little toy motor where a magnet comes by, causes an induction, turns on a transistor, and it produces a pulse back out. And somehow some of this energy, even though there doesn't seem to be a current loop here when this is off, some of this energy seems to be forced back into the battery to make it last a very long time. Down here we have the DC to DC converter, and here we clearly show that the battery is charging and discharging an inductor, and we have some sort of little pulse train turning our transistor on and off, and then the current is all shunted over and charges this capacitor here. So again, these things are getting very, very efficient. You can buy little chips now that operate in the 93-94% efficiency for little circuit boards and things for DC to DC step-up situations. And this is a boost converter. Here we have John Bedini's basic circuit. This is the circuit that's been all over the internet for quite a long time. And this is what would be called the simplified schoolgirl motor patent. And again, showing the very extreme similarity to a simple DC to DC converter. Got the battery charging an inductor, turning on and off. You've got a winding that shows some sort of feedback mechanism when the mechanical trigger comes by. And then instead of having a common ground between the supply and the eventual collected energy, he shows a split situation so that basically this battery and this battery are not in parallel, they're actually in series. And so what happens is that this, over here in the DC to DC converter, this draws power all the time. So whether this is charging the inductor or discharging the inductor, current is coming out of this system all the time. Whereas in this situation, it acts more like a bucket and dipper system, where a charge will come out of this battery, it will charge this inductor, and when this shuts off, that ends the current loop with the charging battery, and then this becomes the source, and it discharges into this battery. So it basically it scoops some energy out of here, invests it in creating the magnetic field. That magnetic field then can do work on the wheel, and then when this turns off, this discharges and is as much of it as can be recovered and is put into the second battery. So now let's take a look at Bob Thiel's circuit and see if any of these types of activities could be going on, and it looks like they could. Here he has his basic mechanical contactor as a commutator here, and so when this is shut, the solenoid will turn on and it will draw in the iron, and then when this turns off, this is going to want to discharge. Now what happens is that in this particular case, when it's charging, when it's becoming magnetized, this is the positive end and this is the negative end, because that's how they lay the battery on it. But as soon as the connection is not made, what happens is that the lines of force are now collapsing, and they're cutting the wires in an opposite direction. So the polarity of the coil switches. You saw it switch here when this was negative before and this was positive when it was being charged, but when it discharged, you can see it's the opposite direction. So that will happen here too. So now all of a sudden this is in series with this, and doubles up on the voltage. And what that can do is it can charge this capacitor very quickly. So this not only acts as a snubber arrangement to suppress sparking here, but it can also act as a small storage system that can transfer energy in an AC pulse. So if this charges up to many times higher than the battery, and then, so if this is positive and this is negative, then this is going to be the negative side of the capacitor, and this is going to be the positive side of the capacitor. So this side of the capacitor rises to many, many times the battery voltage. And so it's possible to transfer a pulse of current in the charging direction back to this battery using this circuit. So it is possible when this system turns off that this system can kick back some of the energy back to the battery to make his battery last a very long time. So this may be one of the things that Bob Thiel was doing to make his motor perform with the superlative performance characteristics which he was describing. Now we saw on the bench that you could get a certain amount of the electrical energy back out of the machine. But to get up to the level of performance that Bob Thiel's talking about here, we probably have to look very carefully at his solenoid design as well. Because we saw that the more you folded the magnetic energy down into a closed path around the movable member, the more mechanical energy it produced without having to put any more electricity in. And we saw that on the bench. So let's suppose and let's imagine that Thiel figured out how to maximize this process, and that is a very, very important aspect of why his solenoid engines worked so much better than anything else anyone else has ever reported. So here is a close-up shot of one of the four-cylinder machines, and we see here the solenoid, and we can see a couple of things. One, we can see that the movable plunger comes out essentially or up to the top at the end of the stroke. And we can see that the coil is completely enclosed in a magnetic keeper, and that the dimension across the keeper to the movable plunger, it looks like the movable plunger is approximately 1/3 of the diameter of the total solenoid. So let's take a look at some other photographic evidence. So here's a side shot of the 8-cylinder magnepulsion engine model. And if we just zoom right in here, we can see that we can look down the throat of these little solenoids here, and we can also see a side view, and we can see the crank system here. And what we see is that it doesn't look like that these are built on the design from the second patent. And in fact, it doesn't look like that they are that the movable member ever comes out of the structure at all, that this is just the connecting rod in any of the positions. And again, we see that the magnetic keeper looks like it's about 2/3 of the diameter, and the movable plunger is about 1/3 of the diameter. So this suggests that the design that we tried in our motor, based on the drawings from the second patent, really weren't what he was doing. So let's go back to the first patent, because in the first patent there's another drawing that shows a different construction. So here is figure 5 from the first patent, and this looks a little bit closer to what we were seeing in the photographic evidence. The main discrepancy is it doesn't show an open top here, but for the most part it does show that the movable plunger kind of stays within the structure, and that up at the top here, when the throw is all the way to the top, then the connecting arm would be rather deep inside the structure. So let's take a look at one other drawing as part of the first patent. So here are figures 1 and 2 from the first patent, and what I'd like to show you here is if we come in on a real tight shot, we can see that the the solenoid design here is much more similar to the drawings that I just showed you and the actual physical photographic evidence which the pictures of the working model shows. So basically what we have here is a solenoid piece that stays deep within the structure for its entire movement. And so now what we need to do is we need to understand how he gets these solenoids to create so much physical mechanical energy. So let's take a look at the probable internal design of this system. Now we know from the earliest reports of people trying to develop a magnetic attraction engine that the magnetic force only creates a very large physical force when the air gap is the smallest. And the best and the brightest motor designers of the last 170 years or so struggled with getting the topology right. We're quite clear that Bob Thiel figured this out, and here is essentially the essence of what he found. By essentially adding this little extra lip at the top of the keeper here, what we see is that we can turn the coil on at this point. This is the midpoint, the point at which you're at the midpoint on the crankshaft. In other words, where you can apply the most direct tangential force to the crank. And when we turn the coil on at this point, essentially the magnetic keeper is already completely made. In other words, the magnetic field can act at the closest possible range. And this means that the force on our movable plunger here is going to be maximum right from the start. But because there is slightly less iron down at the end here and slightly more iron up here, moving upwards will allow for the creation of an even more advantageous magnetic circuit. And so that is the direction of the force generated. So let me just back out here and let's just take a look at the entire design of the magnipulsion solenoid. So we saw from the photographic evidence and from the diagrams in Thiel's first patent that the movable plunger never really leaves the structure. So here at the bottom dead center of our crank, we can see that the plunger is essentially at the bottom of the structure. And here at top dead center of the crank, we can see that the plunger is essentially at the top of the structure. So that the plunger basically moves within the structure and it stays within the structure at all times. And this keeps the physical side forces and other things at a minimum so that a relatively low friction sliding movement can be generated in here. So what we want to see here is that the situation is designed so that the coil would be turned on when the plunger is halfway through its movement, and because at that point we can apply the greatest tangential force to our rotating member. And to do that, we need the magnetic circuit to be already in its condition where the least air gap exists between the moving member and the non-moving member, and that the moving member can move in such a way that it produces an even more advantageous magnetic circuit as it moves forward along its path. So these are the fundamental conditions which allow the magnetopulsion engine to produce tremendous amounts of mechanical energy for the electricity applied. Now, let me give you just a quick example of what I'm talking about here. We saw in the commutator circuit that his contacts were very, very short. The little nubs on the commutator wheels could only cause those contactors to touch for a very, very brief period of time. So if we imagine, for instance, in Thiel's engine, if this coil here was, say, 200 turns of a relatively large diameter wire, and we dropped a 10 amp pulse across this, even for 1 or 2 milliseconds, what that would do is it would create a magnetic field here that was the equivalent of 2,000 ampere turns. And that 2,000 ampere turns would be in a completely closed magnetic loop, and it would create a thrust vector on this that was extremely considerable. And that would tend to draw this up very, very rapidly. And then when this was turned off, of course, this inductance the magnetic field would collapse again, and that electric pulse could be recovered. So it's important to see over here in the full extension drawing here that this is where the solenoid is trying to get to. We know that if you take any kind of movable piece of iron and put it in a coil, it will always try and center in the coil. And this is true whether there's a keeper there or not. And you can run as many experiments as you want, but the fact is that the keeper, or the movable piece, will try and center itself within the coil. So when we turn it on here, it's trying to get to this position, and it will, if we just left the coil on, it would rise to the top and stay there. So this is the basic secret. This is the fundamental design of Thiel's system, and my reproduction of it, my reconstruction of it. But even if this wasn't the exact design that he used, his design fulfilled these requirements, and therefore it is essentially the same. So now we can put all the pieces together and come up with what I'm calling here for this purpose the Lindemann solenoid engine, because this has features in it which I derived from a number of different sources. First of all, we see that we have this basic structure and we have a crankshaft, but that this, when it turns on, it is the magnetic field's already made, so we can expect that this solenoid is going to give us the biggest bang for our buck when it comes to producing mechanical energy. We have a very simple circuit here, and that this is the run battery, and it goes through the coil and a single transistor, and then back to that battery. And then we can control when it is on using a commutator arrangement, and this commutator could be a brush, or it could be a magnetic reed, or it could be an opto-isolator with a shutter, or anything like that, and or a P device of some sort that was controlled by something else. And then we just have a voltage bridge, 2 resistors here that put a little bit of positive energy on when we want to, and when this shuts off, then this is just a connection back to the negative. So this would clamp the transistor off very rapidly when the commutator went off. So now if we simply apply electric energy in this quadrant here, so we can pull up here, and then we discharge electric energy in this quadrant here, so the magnetic field is rising and collapsing, and we can use the entire magnetic field to cause our attraction process, because it doesn't matter whether it's delivering current or whether it's running on current. The magnetic field is there and the ampere turns are there, and so we can power this motor now not only from the energy that is coming from our run battery, but also it can run on the energy that we are returning to the second battery, because the field is the field, and the field is causing a mechanical attraction process which doesn't really alter the electrical processes much at all. So here is a very, very high COP, zero back EMF electric motor. So learning from Bob Thiel's success, we can now take the idea to its full manifestation of a rotary design and get back to a true motor instead of running it like a piston engine. So here's what I call the Lindemann rotary attraction motor featuring the S rotor. And let me just zoom in a little bit and so we can get a closer view of the structure. Basically, we're using the same circuit as we were with the solenoid engine in the last slide, but now we've replaced the piston and crank mechanism with this, and this basically is just a single coil with a C type of core and what I'm calling the S rotor. And the S rotor is just made out of iron. It could be cast iron or Selectron laminations. Anything that will magnetize to a high degree but then let go of its magnetic field completely when the impressing field is gone. And so what we see is, like the extensions coming down into Bob Thiel's solenoid design, what we have is basically an iron beam here, and we know that if that's all that was there, if we turn this coil on, this would want to rotate around and come in line with this. But now what we do is we put